Hello guys, welcome to the Landis Performance channel. In this video I will be assembling this very trick Atlas 4200 race engine. This engine belongs to Leo Santucci, the writer of two books, Chevy Inliner 6-cylinder power manual editions 1 and 2. This engine usually resides between the frame rails of his 1954 Studebaker drag car. This engine originally built by Self Race Engines for John Cunningham's Chevy II wagon, which ran in this 2005 Hot Rod Drag Week. In Leo's Studebaker, it has been as fast as 818 at 170 miles per hour in the quarter. But we're looking to make this the world's fastest 4200 in a door car, so we are looking for the 7-second zone. So check out as I show the engine being completely assembled from start to finish, all the trick parts and building procedures on the world's fastest Atlas 4200. Anyway, I figured we would go over some of the stuff that we're doing and using for this project. This engine was originally built by Self Race Engines, and it has a turbo on it. So as you can see, the deck has been welded. It has large sleeves installed. A couple other things, this is a dry sump engine. So the oil filter area has been all plugged off and all of our oil goes in through this assembly here. The bottom of the engine, we're using BMW ARP studs. The studs that were originally in the motor were custom made and broke, and we weren't able to do anything with those. Another thing that we've done is down here. See if I can get a close-up on that. I've added a oiler to the thrust bearing. We've had issues with this engine eating the thrust bearing up, and this is a common thing that we've done in the past. Put a 10-30-second hole or a 10-30-second thread in the block to the main oil galley with a restrictor. This one happens to be a 40 thousandths, and that will pressurize the thrust bearing to keep the the torque converter from pushing against the thrust and eating the bearing up when trying to get the turbo to spool. Now, the way the Self Racing did this block is it has this custom girdle and spacers. That's why the studs are not the same length as a production unit. So that all goes on along with the caps and the bearings. In this engine we're using Bill Miller rods and a JE flat top piston, gas ported, and using CP rings. So we're going to go ahead and install this, get this assembly installed. We've already checked bearing clearances and we file fitted the rings. Just for record, we file fitted the top ring at 25 thousandths and the second ring at 28 thousandths per manufacturer spec for turbo engine. And we're running 3 thousandths oil clearance or bearing clearance on the mains and the rods. And for the crankshaft, we're running a production 2002 crank. Now, considerable work was done to the crank where all of the journals were knife edged, and they machined the tooth wheel off the throw of the crank because we're running a crank trigger with a cam sensor and Holley EFI with a Dominator computer to control everything. So this crank was done by Self Racing, and we're going to reuse it. I think the next time, this one uses a 2-inch small block Chevy small journal bearing. They've ground the crank down. I think for our next engine we will not do that. We'll probably, in fact, our next engine will probably be a steel rod engine. But this is the way the engine was originally designed by Self Racing, and we're going to go ahead and wash everything up and get it assembled. All right, so because these connecting rods and bearings are from a small block Chevy, they're normally rod to rod in the orientation in the block. So the bearing surfaces to the edge on one side of the rod, and they're narrowed on the opposite side. Being this motor, they're single rod on each journal, we had to make this fixture to narrow these bearings. So we put the bearings in the fixture goes together, and then we can cut the surface off even with the block, and that makes the bearing the right width for this application. Okay, so now that the fixture is tight, you can see how the bearing is hanging out. That's what we have to cut off. So let's go ahead and do that. As you can see, now the bearing is the proper width for our application. And we'll take it out of this fixture. We have to put it in another fixture to drill it for the dowel pin for the aluminum connecting rod. Okay, so we use this manually fixture to drill the connecting rod for the dowel pin. So you get your lower bearing in, stick it in the tab, line it up in the drill press, clamp the piece down, a little dab of oil. You want to put even pressure on it, and when you feel it to start to go through, you want to back off. And that's it. Hole drilled in our bearing. Now we'll deburr it. Be closer to assembling. To polish the bearings, we use mineral spirits, and we use 4O steel wool. Take the bearing one and get all the dirt and stuff out of it. So some mineral spirits on there and just polish away. And after polishing them, they come nice and clean like that. Takes the coating off. Finish polishing these bearings and we'll be ready to assemble the engine. All right, so after machining the bearings and polishing them, you can see here how there's a radius on both sides of this rod because the rod is a single rod between journal throws. So there's a radius on both sides. So narrowing the bearing allowed us to have that radius on both sides. And of course polishing. So I've got 5 pistons in. I'm figured I'd do the last one real time so you can see exactly the procedures we do to go through that for the installation. So first we'll take a clean rag, put some lacquer thinner on it, and then we'll wipe the cylinder down to get all the last little fragments out of the cylinder wall. And you can see, even though the motor's been washed, there's still quite a bit of crud left in the cylinder walls. Now we'll do it one more time, make sure we get all the crud out. Looks pretty good there. We take our BR braking oil in. I like using this because it's got special properties for helping aid in ring seal. And that's what we'll use in the motor on the initial fire up. So I like to put a small coating of oil on the rings so that they have some lube on it for the startup. You don't want to drench them in oil, you don't want to dunk them in oil, you just want to kind of wipe oil on them like that. These rings have a, you probably can't see that, but there's a ring support because the wrist pin is going through the piston. So we want to find that gap, which is right there. So we want to start our rings on this 180 degrees from that. All right, so we put our expansion rails on. I already did it. The battery went dead last night, so we're starting over again today. So we have our expander rings touching, and then at 45 degrees, we put the 2 oil rails in and get that all centered. Now, our gaps are here, so we're going to turn the rod 180, and this is where we'll put our second ring on. You always look at your ring. There's usually a mark that shows up. Use our expander. And goes on like that. Now, for many years, I used to spin my rings on, but I've learned over the years that there's a couple problems with that. First of all, with the 3/16 ring, it's got a lot more structural integrity, but a lot of times as it's going on, you're peeling off a little piece of piston at the ring groove, and that can actually go down and embed in the piston and stick the ring in the piston. So that's not a good sign. So using an expander is a much better way to go. So now we put our gap on here, we spin the piston 180 degrees again. Again, we look for our top mark. And put the ring on. And this way, there's no material getting stuck in the piston. The rings are free. Another good thing, I'm not sure if you can see, but this ring is a dark ring, and that one has like a finish on it. So your finished ring is always going to go to the top. That's always going to be your top ring. And the second ring is usually a ductile iron where it's got that grayish black look. So now our rings are set. Take a little bit of oil, we lube up our ring compressor. Make sure our rings are equally in the grooves. Take our bearing guard. Put a generous amount of bearing guard on there. Now we've already lubed the cylinder with the Joe Gibbs BR. When everything's right, you just push the piston in like that. The journal is up, the rod's tight. We go through the same process. Bearing guard, a lot of it. And then put some motor oil on the bearing, or on the bolt, and the washer. Run them down finger tight. Snug them down. We take our torque wrench. On most aluminum rods, you're supposed to pull it in one clean pull. These rods go to 75 foot-pounds. All right, so they're torqued to 75. Paint them. That way we know later on that they've been torqued. And the other thing I do on every piston I put in, I rotate the engine. You know, if there's a ring that gets overlapped or a tight bearing, you feel it in the drag. This one actually has almost the exact same drag with all 6 pistons in it as it had with none. So the short block is now complete. All right, so before we can put the head on, we want to get the valves adjusted. It's much easier to do it on the bench, one cam at a time, and you just go and adjust it. So this engine, being a race engine, uses these Jessel solid tappets. They are 2-piece, they come apart, and in between here, they use these shims. And we have a bunch of different sizes from 3,000s all the way up to 28,000, actually 32,000s. So you put a stack in there and you adjust it, valve lash, and then adjust. So you end up with a worksheet like this. So there's our first adjustments. There's the amount of shim change. Then we go back and do it again. And we keep doing it till you can see the final row on the intake. We ended up with 7 to 9 thousandths. Our target was 8. So now we're going to do the exhaust the same way. We're going to measure it, write down what the correct valve clearance is with feeler gauges, and then we'll take the cam back out and then adjust the shims to get us to our destination. On this side, we're going to go between 9 and 11 thousandths because our target is 10. So that's how it's done. It takes a little bit of time, but it has to be done, and to get the engine to run 100%, you want it to be correct. So, all right, so we clean the block surface and the deck surface of the head with lacquer thinner. We put our Halimar copper gasket on there, and now we're ready to bolt it down. Now, because the LS stud is a little tall, we use these spacers to fill in the difference. And then we'll put ARP lube on this, Molly, and we'll torque it. All right, so we put the head on. We have our spacer, It takes up the difference because the studs are about 1 inch longer than we need. And then, of course, we painted our bolts to show that they're torqued, and we torqued them to 85 foot-pounds. The copper gasket got a good squeeze on the Halimar. So now we're ready to put our rocker arms in and our camshaft. And these cams are regrind from Comp, 5.5-inch lift. And then this is the cam gear that self-made for the intake, and that's the cam gear for the exhaust. And we'll put high pressure assembly lube. We use high pressure assembly lube on all the pivot points, the valve tip and the lifter stud. And the rocker arm is a Jessel rocker arm. Okay, so we put our camshafts in. We use this tool modified for the studs to put the cams in at the correct location with the motor on TDC. We put our timing chain on. Now, because of the modified gears, we had to make our own pointer spots where the links go. So we've installed our degree wheel that even a blind man can see. And we have our hub set up. Now what we'll do is we'll put a piston stop in. We'll roll up against the stop, go 360 against the stop the other way, read both spots on the wheel, divided by 2, and that makes true TDC. And then we'll degree the cams. So that's what we're gonna do now. All right, so we have our stop in. We rolled the motor and it stopped at 15 on the wheel. So now we'll roll the motor over the opposite direction. And it stopped basically 26. It stopped at 15 and now it stopped at 26. So we're gonna set our wheel at 20 and a half. And then verify it. And there we go, 20 and a half. So now we've found true TDC of this engine. I didn't show the stop before. It's basically just a spark plug. We put it in the lathe, took the porcelain out and tapped it and put a bolt through it. So because the engine is aluminum, I have a steel plate that I use for my magnetic dial indicator. And on my dial indicator, I've got a long rod that I fabbed up years ago. I need to make a new one, a little prettier one. But anyway, it works. That'll get up over the camshaft. And you want the dial indicator to go straight down with the valve. You want it in line so that it doesn't have any difference in angle or anything like that. Okay, so with many times adjusting cam timing, checking valve to piston, we've got this thing all dialed in. Now this motor does utilize a manual adjuster on the tensioner, but our valve to piston is good and our cams are set 103, 113. We have 50 thousandths valve to piston on the intake and we have 100 on the exhaust. So now all that's left to do is the rest of it. Now we have to put the front cover on, rear cover, oil pan, intake, exhaust manifold, and we get to put it in the car. So stay tuned. And there we go. Engine assembly is complete. Next I'll install the engine into the Studebaker engine bay. At that point I will check converter end play and adjust, install the intake, the exhaust header, the turbocharger, radiator, and intercooler, and reconnect all of the Holley EFI harness. Then prime the oil, add fuel, fire this bad boy up. I will be dropping those videos soon, so keep an eye on the channel for those. Thanks for watching the assembly of the world's fastest 4200 engine in a door car. Sit.